Have you ever wondered what makes cars move or how motorcycles roar down the streets? The answer lies in a marvel of engineering known as the internal combustion engine. This ingenious invention has been powering our world for over a century, and its impact on transportation and industry is undeniable. In essence, an internal combustion engine, or ICE, is a device that converts chemical energy stored in fuels like gasoline or diesel into mechanical energy. This conversion happens within the engine itself, hence the name internal combustion. The mechanical energy produced is then used to power vehicles, generators, and countless other machines. The most common type of ICE is the four-stroke engine found in most cars and trucks on the road today. Its operation relies on a cyclical process known as the four-stroke cycle, which we'll delve into next. Understanding this cycle is key to grasping how engines work. The four-stroke cycle is a beautifully orchestrated sequence of events that occur within the engine's cylinders. Each stroke represents a distinct movement of the piston within the cylinder, and together they form the foundation of the engine's operation. The cycle begins with the intake stroke. Imagine the piston at the top of the cylinder. As the piston moves downwards, it creates a vacuum within the cylinder. This vacuum sucks in a mixture of air and fuel through the open intake valve, much like breathing in air. With the air-fuel mixture inside the cylinder, the intake valve closes tightly. Now the piston moves upwards, compressing the trapped mixture. This compression is crucial as it increases the energy potential of the fuel, making the combustion more powerful. This stroke is where the magic happens. With the air-fuel mixture compressed, a spark ignites the mixture, causing a controlled explosion. This rapid expansion of burning gases pushes the piston downwards with great force, generating the power that drives the engine. After the combustion, the piston moves upwards once again, this time with the exhaust valve open. This upward movement forces the burnt gases out of the cylinder and into the exhaust system, completing one full cycle. The cycle then repeats, starting again with the intake stroke. To truly appreciate the ingenuity of internal combustion engines, we need to understand the key components that work in harmony to make it all possible. These components, each with a specific role, are the building blocks of this remarkable machine. Pistons are cylindrical components that move up and down within the cylinders. They are the engine's workhorses, directly experiencing the force generated by the combustion process. Cylinders are the chambers within the engine block where the pistons reside. They provide the enclosed space necessary for the four-stroke cycle to occur. The crankshaft is a rotating shaft that converts the linear motion of the pistons into rotational motion. It's connected to the pistons through connecting rods and acts as the intermediary between the engine's internal movements and the vehicle's wheels. Valves act as gatekeepers, controlling the flow of gases in and out of the cylinders. The intake valves allow the air-fuel mixture to enter, while the exhaust valves release the burnt gases. Found in gasoline engines, spark plugs are responsible for igniting the compressed air-fuel mixture. They generate a high-voltage spark that initiates the combustion process, leading to the power stroke. The true marvel of an internal combustion engine lies in its ability to transform chemical energy, locked within fuels, into mechanical energy that propels our vehicles and powers our world. This transformation is a testament to the ingenuity of engineering and the principles of thermodynamics. It all begins with the combustion process. The air-fuel mixture, compressed within the cylinder, contains a significant amount of stored chemical energy. When the spark plug ignites this mixture, a rapid chemical reaction occurs, releasing a tremendous amount of heat and expanding gases. This expansion of hot gases exerts immense pressure on the piston, forcing it to move downwards. This linear motion of the piston is then converted into rotational motion by the crankshaft, which is connected to the vehicle's transmission and ultimately to the wheels. Thus, the chemical energy stored within the fuel is transformed into mechanical energy, enabling the vehicle to move. This continuous cycle of combustion and energy conversion is the heart of how an internal combustion engine works. Section 5. Gasoline versus diesel, a tale of two engines. While all internal combustion engines operate on the principle of converting chemical energy into mechanical energy, there are distinct types of engines, each with its own characteristics and applications. Two of the most common types are gasoline engines and diesel engines. Gasoline engines, found in most passenger cars, rely on spark plugs to ignite the air-fuel mixture. The spark provides the initial energy to start the combustion process. These engines are generally known for their higher revolutions per minute, making them suitable for applications where quick acceleration and high speeds are desired. Diesel engines, on the other hand, don't use spark plugs. Instead, they rely on the heat generated by compressing air to extremely high pressures. When diesel fuel is injected into this hot, compressed air, it ignites spontaneously, eliminating the need for a spark. This difference in ignition methods gives diesel engines several advantages. They tend to be more fuel efficient, delivering more miles per gallon, and they produce higher torque, making them suitable for heavy-duty applications like trucks and machinery. Section 6. The environmental footprint of combustion. While internal combustion engines have revolutionized transportation and industry, their operation comes at an environmental cost. The combustion process, while essential for generating power, produces emissions that contribute to air pollution and climate change. One of the primary concerns is the emission of carbon dioxide, a greenhouse gas. During combustion, carbon in the fuel reacts with oxygen, releasing carbon dioxide into the atmosphere. This contributes to the greenhouse effect, trapping heat and leading to global warming. In addition to carbon dioxide, internal combustion engines also release other harmful pollutants, including nitrogen oxides, particulate matter, and unburned hydrocarbons. These pollutants contribute to smog, respiratory problems, and other health issues. Over the years, regulations and advancements in engine technology have significantly reduced emissions from internal combustion engines. However, the environmental impact remains a concern, prompting the development of alternative powertrain technologies. Section 7. The future of engines. The automotive industry is undergoing a significant transformation, driven by concerns over climate change and the need for more sustainable transportation solutions. While internal combustion engines have dominated the market for over a century, their future is being reshaped by the emergence of electric vehicles and alternative fuel technologies. Electric vehicles, powered by batteries and electric motors, offer a zero-emission alternative to traditional gasoline and diesel vehicles. As battery technology improves and charging infrastructure expands, electric vehicles are becoming increasingly popular, challenging the dominance of internal combustion engines. Furthermore, research and development efforts are focused on exploring alternative fuels like hydrogen and biofuels. These fuels have the potential to reduce or even eliminate greenhouse gas emissions from vehicles, paving the way for a greener future. The future of engines is likely to be a mix of different technologies, each catering to specific needs and applications. Internal combustion engines, with their established infrastructure and continuous improvements in efficiency and emissions, will continue to play a role, especially in heavy-duty vehicles and applications where electric powertrains face challenges. Section 8. Conclusion: a journey of innovation. The internal combustion engine stands as a testament to human ingenuity, a complex and powerful machine that has shaped our world in profound ways. From powering our vehicles to driving industry, its impact is undeniable. Understanding how these engines work, from the fundamental principles of the four-stroke cycle to the intricate interplay of components, allows us to appreciate the engineering marvel that lies beneath the hood. As we look to the future, the automotive landscape is evolving, driven by environmental concerns and technological advancements. While the dominance of internal combustion engines may be challenged, their legacy of innovation and their continued relevance in specific applications ensure that they will remain an integral part of our technological landscape for years to come. For those eager to delve deeper into the world of engines, exploring the intricacies of different engine designs, advancements in fuel efficiency, and the quest for alternative fuels offers a fascinating journey into the heart of automotive engineering.